File. Oh, you need me to pull it? Or do you have it on thumb drive? Okay, that'll work. You're right there. You just write with it like you normally would. Not that then. Use this one. And it runs just like any other pen.
Okay, thank you.
Content. And the one.
Okay. Good morning, class. My name is Jesse.
Keep going.
My name is Jesse, and today I'll be giving a presentation on highway drainage for this CEE class. So, beginning, we'll go to the learning objectives. I hope that's by the end of this presentation, you have an understanding of these points listed here to understand the importance of drainage on our highways, identify the various components that are involved in surface drainage, and also apply hydraulic calculations to various surface drainage components. There are lots of things involved, but we have to limit the slides because of time. And also the main reference documents I'll be using for this class is the Hydraulic Engineering Circular number 22, developed by the Federal Highway Administration. It's a guide on how to design surface drainage components for urban areas. The reason for urban areas is because of the limited right of way available. Because in rural areas, there are large areas of land, so they don't really use that much of curbs and gutters, and they are more used to using ditches. But in urban areas, due to the limited right of way, they have to make use of various curbs and gutters and inlets to be able to drain the water from the roadways. Okay, so first of all, I want to understand the importance of highway drainage. So these are some of the points listed of why, as a highway engineer, you have to value the concept of highway drainage, such as pavement management. As quickly as you can remove water from the surface, it prevents it from infiltrating into the top the coarse materials on the road. That weakens the bonds on the surface, making the roads less last long. So the more quickly you can remove the water from the road, the more you are likely to have a longevity on the roads. Second is traffic safety. Preventing hydroplaning. We have talked about hydroplaning plenty times in this class. The less water on the roads, the less likely you are to get involved in various accidents. Also, the less water on the roads, the more you are likely to see various road markings to be able to help you make decisions, especially at intersections. So the less road water on the road, the more visibility it has, helping you to make better decisions at intersections. Also, erosion prevention. This is very important in areas of both cut and fill. The more you are able to treat the drainage well, the less you are likely to deteriorate the road from erosion from water. And as I said earlier, the more you're able to prevent water from staying longer on the road, the more the road lasts long. And also maintenance costs. If you're able to design your roads well to handle water, the less you spend on doing various things like patching potholes, fixing the sides of the road to prevent erosion. Okay. So these are some of the impacts of poor drainage That's you have to know, so that you realize that when you see these things on roads, you realize that they have been caused by the roads having poor drainage facilities, reduced pavement structural capacity. As the water stays longer on the roads, there are certain areas where the water pumps and the roads deteriorate much faster in those areas. Subgrade failure. This has to do with subsurface drainage. We have surface drainage and subsurface drainage. Subsurface drainage has to do with the water beneath the pavements. That's the water level. If you are not able to treat the water level by preventing it from meeting the base, the sub base, it also has impacts on the overall longevity on the road. Accelerated deterioration, I've talked about that. Reduced skid resistance. This is important during heavy rainfall. You want your cars to have good contacts with the road surface in case you need to make emergency brakes. But as more water gets ponded on the road, you are less likely to have that contact with the road. Also, I've talked about increased risk of hydroplaning, slope instability. That's along the edges of the areas where embankments have been made. The more water stays in those areas, the more it erodes the overall stability of the road, making it less safer to use. I've also talked about damage to embankment slopes. These are some of the images of areas where there are some poor drainage. The first image when I clicked on it, it went back. I wanted to highlight something. Yeah. Okay. But I think I wanted to highlight this area. As a car is coming this way, you realize that a part of the road is ponded by water, so they would want to escape. They would want to veer off into the lane of the opposing vehicles to try and prevent from having contact with the car. That makes it risky for those in the coming lanes too. So it reduces road safety. Also, this area to realize that this part has deteriorated more, entering the road surface. If it's not worked on, it will continue eroding into the roadway, making it less safer. Just like the first picture, more people will be wanting to make turns to avoid hitting those potholes. And thirdly, an image of a car in the process of hydroplaning, showing that the vehicle has less resistance on how it moves on the roadway. As I said earlier, for the drainage systems, for managing for highway systems for managing drainage, we have two major areas. We have the ones that's on the surface and the ones beneath the surface. So the surface is mostly concerned with removing and diversion of water from the surface of the roadway. That's how things such as ditches, gutters, curb inlets, all combined, and also cross slopes all combined together to help drain water from the road surface. And we have subsurface drainage that helps with diversion and removal of excess soil water from the subgrade. So basically, we are trying to prevent the existing water in the water table from going to a height that's able to affect the structural quality of the roadway. So there are various things that can be done beneath the surface of the roadway to prevent these things from happening. But for this presentation, I'll be focusing mostly on surface drainage systems. These are some of the components of the road that make up the surface drainage components. So we have the shoulders, side slopes, we have the cross slopes that also help drain water along the roadway. We have side ditches and channels that can be located either at the median or on the sides of the roads. We have curbs and gutters that's along the road shoulders to also help drain water from the road surface. We have catch basins and inlets that are all part of the systems that take water from the curbs and gutters and transfer it to various outfalls that are outside of the roadway systems. And we have culverts. Culverts allow water to cross roadway sections, areas where the water alignment and the road alignment meet. You can create culverts to allow the water causeway to pass through without interfering with the roadway. So this is an flowing gutters. So for the surface drainage systems, I'll be talking about gutters. And these gutters, we have two main components. We have the ones that have a uniform cross section and the ones that have a composite cross section. So a uniform section will have something like this. This section has a constant slope throughout. That's what you describe as. So this will be the height of the gutter, and this will be the slope. Let's say S. Let's go.
The little copper button.
Oh, okay.
That's what's bringing some of the stuff.
SX of the road. It has a continuous slope throughout the section, but for a composite gutter, there are two combinations of slopes. We have one that's shallow, let's call it SW, and we have one that's much steeper, SX. They are all used for various reasons, but the composite gutters are preferred by a lot of agencies due to the fact that it's much safer for pedestrians, especially for cyclists. Because of this section, you can limit the width of this section that has a deep slope along the edges of the curb and have this shallow slope along this area that can be used by the cyclists. But for the uniform cross section, it has to the slope has to continue towards the edge of the travelway. That makes it much difficult for cyclists to use those road sections. So this is an image of some of the parts of okay. Here's an image of some of the parts of the various components that we consider for flow in gutters. So we have the longitudinal slope. That's a component of the roadway that's designed when you are working on vertical curves. We have the catchment runoff. That's rainfall from the various areas outside the roadway, areas along the edge of the roadway that's directed towards the gutters. We have the spread. The spread is a measure of how far the water enters the road, the travelway during rainfall. That's one of the most important things we look at when we are designing for flows in gutters. We want to limit the spread as much as possible by designing the gutter in ways that you limit the spread as much as possible so that travelers can use the roadways without interacting with the water from the rainfall. Also, we have the gutter width. That's how wide the gutter is from the edge of the curb. We have the great inlets. So along the gutters, you need ways to remove it from the gutters. The gutters collects the water from the roadway, and the inlets collect water from the gutters. So it's like a uniform system where after the water gets into the gutters, it continues into the inlets. And we have various types of inlets that we'll be talking about later. And there's this thing called intercepted flow. As the water moves from this section coming here, there's a section of the water that's intercepted and enters the inlets, and there's some that's continued along after the inlets. So the water that's intercepted by that inlet is what is referred to as the inlet flow. I think I've talked about everything. Okay, so let's go to calculating for flow in gutters. So this formula is derived from the Manning's formula that I think you have learned about in class. Yes, so these are the various sections that are important to us. What we want to really understand are these these two, the spread and the flow. Because we have a limiting value of the flow, that's called the allowable spread. The allowable spread is the maximum width of water that's allowed onto the roadway from the edge of the curb. And the allowable spread is determined by the various state agencies, and it's also determined by the classification, the functional classification of the road. So arterials and collectors have different allowable spreads, and so do local roads. So we want to make sure that whenever we are designing our gutters, the spread is always less than the allowable spread, so that we are sure that regardless of what flow will be coming in the gutters, the flows that will be coming from the rainfall, it won't affect the traffic movements of people using the road. Any questions? You have a question?
That's supposed to be the location.
Yes. These are all multiplications.
Did they design for spread or for the flow rate?
Usually you have the flow rate from hydrological calculations, so you have an idea. So now you have to control this to make sure that this particular spread is less than the allowable spread, because this is the slope of the gutter. Hope you get it. So it's like an iterative process. So let's say you use a cross slope of, you already know the kill from various calculations about the catchment and things. So you have a general idea of how the rainfall within that area will be like. So you have this value already. So let's say you assume a slope of, let's say, 2%, that will be 0.02. So you have the flow already. This is a constant of 0.56. This is a Manning coefficient that's based on the material you are using. There's a longitudinal slope that's given by the slope of the road. So you already know this. So it's like, this is what you are trying to find out. Given this slope that we have created. So when you arrange this formula, you get this. This formula that allows you to estimate whether the slope you chose for the gutter is less than the allowable spread or it's greater. If it's less, then everything is okay, then you move on. If it's less than, then it means that everything is fine, then you move on. If it's greater, then it means that you have to change the value. Hope you get it. So we have an example here that's given the following parameters of the Manning's coefficient of 0.016, longitudinal slope of 0.010, cross a slope. So this one we are assuming the slope of the gutter is 0.020 and the constant of 0.56. Find the spread when you are given a flow of 1.67 cubic feet per second. And assuming that the allowable spread given by T dot is 8 feet, we want to know whether for this particular slope of the gutter we have chosen, whether it meets the requirements given by T dots. And also the second part is to find the flow when the spread is 7.5. Any answers for the A?
8.8. I don't know how many digits.
And a B.
Yeah, it's got 8.8.
How about the B side? Okay. So let's go on and try and calculate. So we have our T here. Our Q is 1.67 by 0.016. Our K sub U is 0.56. Our slope is 0.020 raised to the power 1.67. Our longitudinal slope is 0.01, 0.010 raised to the power 0.5. Or raised to the power 75. It gives us a spread of 8.8. Since our spread from this selected slope is larger than the allowable spread given by T dot, we have to go back and select another value to make sure that the value we are getting for the spread is less than the allowable spread before we can move on to make sure to know that for this particular flow, our spread is within the requirements given by T dots. So for the second part, 0.56. T was 7.5, raised the bar 2.67. Wow, that's clear. Any questions?
So just make sure I'm understanding this. So we solved for the spread and if that was 8.8, so that was too large. So we
Yeah.
brought the spread back down to 7.5 because that was within the standard.
No, this is just a different question.
Okay.
So in case you want to find a Q bar, you already have a standard spread already.
Got it.
But if you were to go back, you'd have to change the slope.
Okay.
Find another value and replace it in the formula and calculate it again before until you have a value that's less than 8. Any other question? Okay, so going on to inlets, as I said earlier, the inlets and the gutters work together. The gutters collect water from the roads, they transport it along the longitudinal slopes, and the inlets work as interceptors and intercept the water in the gutters and take it underground to connect it to various underground systems onto various outfalls. And we have mainly 4 types of inlets that's mostly used. We have the great inlets, that's this metallic objects that we see a lot around campus. And we have the open cap inlets, that's just an opening along the edge of the curve that allows water to flow into the from the road surface. And we have the combination, that's a combination of the curve opening and the great inlets that provides more interception capacity. And we have the slotted inlets that is usually used for areas with less rainfall that needs to be intercepted. Areas such as parking lots, they are mostly used in areas such as parking lots. Continuing. So we want to see how we design the curb inlets. We have already seen how to design the gutters. We want to continue to see how we design the curb inlets. So the curb inlets are placed along the longitudinal slope of the curve. So assuming we have a curve, a vertical curve of such nature, we'll be playing our curb inlets at various locations such as this to help intercept the flow coming in this direction and flow coming in this direction. So there are 2 major areas where you design for the inlets placed at the bottom of the vertical curves. In the side curves, you realize that they have a bottom part. So you have the curves that are placed down here. Their design process is different from the curves that are placed on grade along the tangents of the vertical curves. Any questions? Because the reason why we design the ones in the side curves differently is because they are intercepting water from 2 directions. They are intercepting water from this direction and water from this direction. So their design is different from looking at the ones along the grade line that intercepts water just flowing in one direction. We also have the thing called the bypass flow. That's you realize that before I talked about intercepted flow. That's the water that's actually collected by the inlets, but some will flow over the inlets onto the next inlet. So that volume of water is called the bypass flow. Okay, so when you are designing, want to talk about designing inlets, the curb inlets on grade. So these are some of the questions we want to answer. So we want to know how long should the inlets be to capture 100% of the gutter flow. So assuming you have an inlet along the roadway like this, you want to know how wide should your inlet be to intercept all of this water coming in. That's the first question we want to know. That means that the bypass flow will be 0. Means that for where it's positioned, all the water coming in enters the curb inlets. We also want to know for an inlet of length L, we realize that this is the best case scenario. That's an inlet opening that's intercepting all of the water. But due to financial constraints, these lengths are usually quite large. So what is how do I put it? What is an ideal efficiency that we want? So that when we have an inlet of length L, it will be okay with us. So let's say we have an inlet like this. We want to know that if we want an inlet efficiency of, let's say, 0.95, it means that for 100% of the water coming in towards the inlet, it intercepts 95%, and the bypass flow is roughly 5%. So if, let's say, you want an inlet with an efficiency of 0.95, what will be the length? So that you have an idea of how the inlet system is working. This is an ideal condition that is really difficult to work out in the field. So usually this is what is done. And finally, you want to know the required spacing for this particular inlet efficiency. So let's say we have already understood that we want an inlet of an efficiency of 95%. How far should we space our inlets along the longitudinal slope of the road such that it captures all of the water? So let's say we place an inlet here, another inlet here. What is the spacing in between? What is the spacing D in between such that when the flow is able to get here, the same efficiency of 95% is maintained? So it's this L and this D that is used in the field. You know you state an efficiency you want, you use it to calculate your L, and from that L you use it to space your inlets along the longitudinal slope of the road. Hope. Any questions? Okay, so this is the formula for the ideal condition of capturing 100% of the gutter flow. You realize that there's also a K sub U here, but the value is 0.6, and the one for gutters was 0.56. So that's something you should note, that when you are designing inlets, the unit of convention constant is not 0.56, but rather 0.6. The formula works similar to the one for gutters. This value is the longitudinal slope of the road. This is the slope of the gutter. The N is the Manning's coefficient, and the Q is the flow in the gutter. But as I said earlier on, this is the ideal condition that's not used on the field because of how high the values we get are. But it helps you to calculate the efficiency as you move on. So we'll go to the question of the efficiency. So we have various ways of calculating our efficiency. You can calculate it based on the intercepted flow, the ratio of the intercepted flow of the inlets to the total flow that's coming. That will give you an idea of the inlet's efficiency. And also want to know the bypass flow, which helps you to calculate the spacing. So let's say the flow coming in is 20 and you are intercepting 15. It means that there is 5 cubic feet per second of volume that's being added to the next inlets along the slope. That needs to be accounted for. So this value is also important to be accounted for. This is another way of calculating the bypass flow using the efficiency. So this is how you get your L value that's used in that field. So first, from the previous calculation, we would have already calculated our L sub T. That is the ideal condition. So we know the value of the ideal condition. Then we would state that the efficiency we want, whether 90%, 85%, or 95%. Then we'll work out to find our L value. So this is the formula that relates the efficiency, the ideal length to the real length that's used in the field. So you work out and make L the subject, then you find out your length of the inlets that you want. Any questions? Okay, so let's go to inlet spacing. Apart from using the longitudinal slope of the vertical curves to determine the spacing, there are standard areas where regardless of the slope or other features of the roof, you have to place inlets at those areas. Areas such as intersections, low points along the gutter grade, that's the sag points. You have to always place an inlet there. And these are some of the areas. The street intersections are very important. You want to intercept any water that will likely get into the intersection. You want your intersections to be free of water as possible to help the drivers make safe turns. So finally, we get to inlet spacing. This is an image to help understand how we calculate this value of D. So we know that these are curb inlets, and we already know the length of the curb inlet L. For this particular situation, we are just assuming that the rainfall coming into the inlets are just from the roadway. We are ignoring rainfall coming from the catchments, areas such as the sidewalks and other areas. For this calculation, we are just assuming that the water is purely coming from the roadway. Hope you get it. So we have this value B, that's the width of the roadway to the crown line. So this is the part of the roadway that moves the water on the rainfall onto the gutter. So let's say we have a roadway like this. This is the length B we are referring to, because it is this width of the roadway that will move the water towards this direction, and this will be the length that will move the water towards that direction. But this value is not always to the center line, because in areas such as along your TRO and SRO, the values will not always be to the center line, but it will be to the crown line, the area of change of direction of the slope. And we have our rainfall rates that can be calculated from various hydrological calculations. Moving on. Okay, so assuming you have two inlets like this. This is the first one on the roadway. This is the second one. The second one will be taking two flows. That's one from just the roadway. That is the Q sub R. This is just rainfall from the roadway from the start of the distance D to the start of the roadway. So this is just the rainfall from this point to this point. Will all be moving towards this inlet. And we have the QB sub up. That will be the portion of the rainfall from this inlet that's not intercepted. That will be the bypass flow from this inlet. So we'll have this portion too. So for any inlets, apart from the first inlet along the longitudinal slope, your flow will constitute flow from the roadway and flow from the bypass flow from the inlet that's upwards of the grade. And if you want to calculate the rainfall from the roadway, you want to calculate this is so your Q from the roadway is equal to this B multiplied by this D multiplied by the rainfall rates to have W multiplied by. So this we are talking about is just the box area here. And the QB up will be from this direction. Earlier on, we realized that we had a calculation that's used the flow and the efficiency to calculate the bypass rates from the previous slides. So basically, it's just trying to find an expression to calculate your D here. So the expression is worked out here. You replace your bypass flow from the upward inlets, you place it here, and you try and find an expression for QR involving Q and E. So now you have two expressions for QR. We have the one from here, that's from the roadway elements, and we have one relating the total flow to efficiency. So you now equate the two and you make your distance between the curves, your subjects. So you end up with this particular formula. And this formula has various elements that you are already aware of. So it makes it easier to calculate your inlet spacing. You have your total flow, you have your efficiency that you know already. You have the weight of the roadway to the crown line, and you have the rainfall rates. So this is how you get the expression for calculating the distance between curb inlets. So let's try and work out this example. Assuming that the discharge from the gutter is only from the rainfall. As you remember, I said that when you are making these calculations, you have to assume that the rainfall is just from the road only. We have a roadway width to the crown line of 12 feet. At a rate, the rainfall is falling at a rate of 1 inch per hour. We have an inlet length of 5 feet, and your ideal length is 6 feet. And you have a gutter flow of 0.19 cubic feet per second.
Okay, we only have 1 minute left, so I'm gonna stop you there. And regarding the homework, I gave it to you already, right? Okay, so it's due Friday. Any questions about inlet spacing and further will be counted as bonus points so that you can improve your home appraisal drawing. So if you can figure it out just by looking at the notes that were provided, then you get bonus points, but you will not lose credit for just skipping.
So are we like, are we considering a personal driveway? Or is it like, yeah,
Turn this in personal problem.
okay, yeah. Got this.
My phone is in my home, it's ringing. Shut down the Teams recording. Okay, all will begin. Oh, it's.
Okay.